Hi everyone. In this video, I want to do a worked example of linear and angular momentum. Here's the mechanism we're going to look at. We have a sliding block that can move in a groove horizontally. There's a pin joint right through the middle of the block attached to a pendulum. This pendulum also has on it a collar. So the collar can slide on the outside of the rod. Kinematically, a collar functions identically to if this pendulum had a groove cut in it and we had a block that we fit into that groove. So the collar is going to slide down the length of the rod. As the rod rotates, the collar is going to rotate with it. Now, one noticeable difference you could have with a collar is you could have some rotation, like a roll rotation around the outside of the rod, and that really depends on the geometry. That could be a square rod, for example, with a square collar on it, in which case it obviously wouldn't be able to rotate. What we're going to say for this one is let's assume that there is no rotation around the collar's long axis. So the long axis being this one, and really what I'm saying is that the collar isn't rolling like this. So what do we want out of this problem? We want the linear momentum of each body. We want angular momentum of each body. I'm going to write the add symbol, but about its own center of mass. And then let's also describe the linear momentum for the whole system as well. All right, before we get started, make sure you're comfortable with each of these concepts, make sure you understand what they mean, and we need to have some kind of game plan for this problem, right? Where are we going to go and what are we going to do? Well, we know that linear momentum, just in a general sense, linear momentum is mass times velocity, and this is velocity specifically of the center of mass for that specific body. And we know that angular momentum is an inertia matrix, or dyadic, multiplied by the angular velocity, the total angular velocity. So I'm just going to say into I, whatever body we're talking about. So this would be the angular momentum of body I about its center of mass, multiplied by the inertia of I, which is the inertia of I multiplied by the angular velocity. So we need to do this for each of the three bodies. And we are going to make some assumptions. We're going to assume that the masses of these bodies are known, and we're also going to assume that the inertia of these bodies are known. If you're the engineer designing this system, well, you spec'd out these parts or designed them in a CAD software or something, so you should know these quantities. All right, so how are we going to build up to this? We need to do position and orientations. We're going to talk about generalized coordinates and constraints and degrees of freedom. It's going to be real simple for this one. From there, we're going to do linear velocity and angular velocity. And from there, we can construct these momentum terms. We can do linear momentum and we can do angular momentum. One thing to take note of, if the problem is asking for momentums, consider that you don't need to do accelerations, because just for the momentums, it's just mass times velocity, and for angular momentum, it's just inertia times angular velocity. So this really just becomes an exercise in kinematics. So at this point in the semester, this should actually be very much review. The only thing new here is really going to be the angular momentum, and I'll show you how to evaluate it. So we need some points. Let's put points in. Point A is the center of mass of the block, and just to make it easy, that's also the pin joint. The center of mass of the pendulum of this rod is going to be point B, and then there is a center of mass C for the collar. So let's go through the kinematics. Yeah, we do need frames on this thing. So the inertial frame, xn, just happens to be aligned with the body attached frame A as well, and its frame A is not going to rotate. And then the B frame and the C frame, if we're saying that there's no rotation of the C frame, then the B frame and C frame are aligned as well. So XB and XC, there is YB and YC. P into A, tell you what, let's go ahead and knock out the rotations. There is no rotation between in frame and A frame. You know how to do that how to show that in your homework. And for the rotation into B, I'm going to do my shorthand. The rotation from N to B is the same as the rotation from N to C. This is a simple rotation of these frames with respect to the N frame about a shared Z-axis, and we're going to give it the angle theta. Okay, so that's done. You've got that in your notes. Position vector from N to A. So block A is going to translate. Let's give it a translation variable Q1 in the x hat N direction. We could have said in the x hat A, they're the same thing. Let's say P A to B. Well, point B is, it's fixed in the geometry of the rod. So this is some length L1 in the XB direction. And let's do the position vector from A to C. Now the collar is going to translate. So we need some translation variable in the XB direction that is going to be Q2 XB. And again, we could have also said that's XC. It's the same thing. And if we, to formally call out the positions of those centers of masses, Pn to B, well, this is just N to A plus A to B, and P into C is P into A plus P A to C. Since we have called out these relative position vectors, this is acceptable. You don't have to explicitly put everything together. All right, next. Let's call out the angular velocities. So angular velocity of A, well, that one's 0. And the angular velocity of B and the angular velocity of C are the same thing. Those are going to be theta dot ZA. Oh, and let's go ahead and do generalized coordinates as well. You can see from the way we define position and orientation, there are 3 generalized coordinates, and it's Q1, Q2, and theta. There are no constraints in this problem, so it is 3 degrees of freedom. And again, what does that mean? That means the values of these generalized coordinates, they're all independent of each other. We could fix the block in place, we could fix the angle, we could hold this, and then we could freely slide the collar. We could take the collar down and I could spin the pendulum, and we could lock this joint and we could freely slide the block. So these are all independent. So we've got angular velocities. Let's do linear velocities. The linear velocity of A, we know that this is ddt of a position vector. And I've erased the definitions, but you've got them in your notes, or just back up the video. ddt of this quantity is going to yield Q1 dot x hat N. VB is ddt of Pn to B. This is going to be, again, you have this position vector, and at this point I expect that you can take these derivatives. So this is Q1 dot x hat N plus L1 theta dot YB, and then VC is Q1 dot xn plus Q theta dot YB plus Q dot XB. This is Q2. There we go. Q2 dot. All right. So we have these. That takes care of angular and linear velocities. At this point, we can directly start writing claims about linear momentums. So, linear momentum of A is MA VA. Now, we've already defined VA. I have it right here. If we want to, we can come in and we can explicitly show MA is equal to Q1 dot X hat N. If you're working a homework problem and I give you dimensions and I give you numbers, then I need you to come in and put the numbers into this problem. So perhaps the mass of A is 5 kilograms and Q1 dot is 3 meters per second. That's fine. This would become 15 kilogram meter per second in the X hat N direction. Don't forget the direction, it's still a vector. So how easy is it now to do these other ones? KB is MB VB, so that is MB multiplied by this expression, Q1 dot X hat N plus L1 theta dot YB. Now, in some problems, it will ask for linear momentum of the body in a particular frame. So let's say that the problem asked for linear momentum of body B in the N frame. So KB in the N frame is going to equal MB multiplied by Q1 dot X hat N plus L1 theta dot, and we need to rotate the YB axis into the N frame. This is where the definitions of rotations come in. So you go to your definition of the rotation and you see that YB is going to equal negative sine theta XN plus cosine theta YN. And if we need the number of it, the numerical value, well, we said that this was 3, perhaps this is 2, and then you have some distance for L1, you have theta dot is 7 radians per second, and you have the current value of theta. And it fits into this, and you crunch the numbers and you solve for it, and there's the answer. And same thing for VC. If we wanted the linear momentum of C, well, that's just MC VC, so KC equals MC multiplied by this. And if we want it in the N frame, you go in and you convert the YB and the XB into the N frame using your definitions from the rotations. That's literally it for linear momentum. And if we wanted linear momentum of the whole thing, we've talked about this, that is K of the system, and that is KA plus KB plus KC. So you just take each of these quantities, and if we actually do want to add them, right, and get a number out of it, then all of these have to be in the same frame. So we turn all of these into the N frame, and then we can just linearly add them all together. And that's it. That is it for linear momentum. So let's move on to the next part. The problem statement says that we want the angular momentum of these bodies about their centers of mass. So let's start with the definitions. The angular momentum of body A about its center of mass, which is point A. So the symbol for angular momentum is H. The first letter is the body. The second letter is the point. So we're looking at the angular momentum of A about point A. The definition of this, it's the inertia dyadic of A about A. These letters are always going to match, multiplied by the angular velocity of that body. So if this is body A, the frame attached to body A is omega into A. Now, we said earlier that omega into A was 0. So that means body A has no angular momentum. Well, because it has no angular velocity, it has no angular momentum. So that one's 0. Next, angular momentum of B about point B. This is IBB times omega n to b. This time, we do know that omega n to b does exist, right? This is going to be IBB times, and we can bring in the theta dot ZB. Next, HCC. This is ICC, omega n to c, so ICC times theta dot ZC. And you can see that I'm changing these, right? I did ZB for this one and ZC for this one. We know that it's the same thing in this problem. Now, if I give you actual numbers in the problem, this is a good place to start, but what do you do with this, right? How do we actually use this information? Let's do the example of HBB. So HBB, geometrically, let's say that it's a cylinder. And you go to, you open up your textbook or you go to an online source and you look it up and you see diagrams of cylinders, and they tell you that they put a frame on this thing, and they give you some equation that says I is equal to 1 over 12 ml squared. Here's what this means. If you have a very thin rod, almost an ideal rod, being that it's the radius has gone all the way down to 0, then this rod has effectively no inertia about its long axis. That means it doesn't take any moment at all to generate angular acceleration because the mass is not distributed very much around this long axis, right? This radius is very small. However, if you were going to rotate around this direction or around this direction, then consider that either way of looking at it, it's kind of like my pen. That's like saying we're going to rotate this way or we're going to rotate this way. Well, if I rotate my pen 90 degrees, that, right, these axes, there's no difference between these axes. There's a noticeable difference when I try to rotate it in this direction. But around these two axes, it's actually the same. So this equation is the inertia about these two axes. In a real cylinder, there is some inertia about this axis, but it's very small. So using this information, what does this IBB actually look like? And how do we build it? Well, if you go back to the video that we did deriving this, we showed that it was a matrix or a dyadic, however you want to think about it. It's a vector of vectors. I said that the diagonal terms, these are the products of, moments of inertia, IXX, IYY, IZZ. And these off-diagonal terms, these are the products of inertia, IXY, IYX, it's actually the same thing, IXZ, IZX, IYZ, and IZY. Remember the properties of this dyadic. The diagonal terms are always positive, the off-diagonal terms could be positive or negative, and it is also symmetric about its diagonal. If we assume that body B is symmetric, we automatically know some things about it. A body that has axis of symmetries, you will see that some of these terms go to 0. If the body is symmetric about all 3 axes, so here is our idealized cylinder. If we cut it in this direction, it's symmetric on both sides. If I cut it in this direction, it's symmetric on both sides. And if I cut it in this direction, it is symmetric on both sides. Same story with a perfect cube, with a perfect sphere, etc. With most generalized geometric shapes, you have these multi-axes of symmetry. What happens to the inertia dyadic is that when you have all these axes of symmetry, your off-diagonal terms are all 0. Because recall what this was. This was the weighted average of all of these position vectors, right? So the distribution of mass in the geometric shape. So if you have symmetric bodies, then you have a bit of mass on this side and a bit of mass on that side, and they cancel out. And a bit of mass here and a bit of mass here will cancel out, etc. So for this symmetric body, here's what's going to happen. Recall how we set up our body frames. We said this was the X for the rod, this was XB, and the YB was in this direction, and the ZB then is coming out. So the long axis of body B is the X, right? So X is the one that's going to have just a tiny little bit of inertia about it. So I'm just going to put in an alpha. Or better yet, since it's a small amount, let's put in a delta. That 1/12 ml squared term, that's going to go into these other two. Now, the reason we know it's in the other two, again, when you go and you look at those diagrams, and they say the inertia about this axis, the inertia about that one, the two axes that are equivalent, right, on my pen, this axis and this axis, the two axes that are equivalent are the Y and the Z, right? And it's the X that's the long axis that sticks out. So that inertia of 1/12 ml squared, it's in these two cases. So here's our IBB. So what about HBB? We got to bring in omega. And I'm just going to change this one to HBB, and this is now IBB. I've drawn the dyadic. Omega into B, we've written it here, but consider it is a vector, it's not scalar. It has dimensions. The dimensions of it are 3 by 1. So we can draw it as 0, 0, theta dot. The theta dot is in the Z entry, which is the third one, and it is not rotating about the X or the Y. So here's your 3 by 3 dyadic multiplied by your 3 by 1 vector. And if you are a bit rusty on your linear algebra, or if you haven't studied it before, the way you perform this multiplication is you take your first row and you multiply by the column, and that's going to equal the first entry of the answer. Now, IBB has dimensions 3 by 3, and then we're multiplying by a vector 3 by 1. The inner dimensions match, so the multiplication can be performed, and then the answer is the outer dimensions. So a 3 by 3 multiplied by 3 by 1 yields a 3 by 1. So I'm going to erase a little bit of that. Oh no. Here's our answer. And this answer is, this is HBB. So you take the first row and you multiply by the column, and we get delta multiplied by 0, and 0 multiplied by theta dot, so this is 0. The second row multiplied by the vector, 1/12 ml squared is multiplied by 0, so this is 0. And then we take this third row and we multiply each of these. So 0 times 0, 0 times 0, and then 1/12 ml squared is now multiplied by theta dot. So 1/12 ml squared theta dot. So what is HBB? I'm just gonna, I got a little room up here, I'll put it up top. HBB, when you perform all of this, is equal to, and I'm going to write it this way. Let's, we said that this was the IXX, and this was the IYY, and this was the IZZ. So this is the IZZ term from the BB dyadic. Sometimes I swap these, it just depends. You might see me write this as IBB, comma ZZ. It's the same thing. Really, this is just, I'm saying it's the IZZ term out of the IBB dyadic. So it's the 3, 3, right? Third row, third column, multiplied by theta dot, because this is now scalar times a scalar. And specifically, what was this IZZ BB term? It's 1/12 MB, right? I left out the, we're talking specifically about the mass of B, times L squared. And pay attention with this L squared. Oh, it's been a little while. I think this is the total length of the rod. So when we said earlier the position vector from A to B was L1, that would make this 2 times L1 squared, and then we could further simplify it down, and we could say that HBB is equal to, this is going to end up being 4 L1 squared, so 4 over 12 makes 1/3 MB L1 squared. So how do you approach these problems? Start by laying out your descriptions. Oh, and don't forget it's a vector, ZB. It is a vector, don't forget that. ZB. Okay. So the angular momentum is also a vector. You can have angular momentum about the 3 different axes, depending on your angular velocity. This body was rotating about a shared z, which means it has angular momentum about the z axis. So what about body C? Without even knowing the geometry of this thing, right? We could model it as, say, a cylinder with the center punched out of it. I can go ahead and tell you that HCC is equal to, and we're going to assume that body C is axisymmetric. This is equal to IZZ from the CC dyadic multiplied by theta dot ZC. And then you would go and you would sort out whatever this was, right, from the geometry, and it becomes just some kind of number multiplied by theta dot in the z hat c direction. Now, it doesn't always clean up this well. Consider that you could have real 3-dimensional bodies with fully populated inertia matrices. So IYY, IZZ, and I'm just going to fill in this third column, IXZ, IYZ. And let's say that we're multiplying by some angular velocity that is theta dot like this, and whatever the entries in the rest of this is. Consider that now, if you have an inertia matrix that does have terms in these directions, now your angular momentum looks like this. First row times this first column yields IXZ times theta dot. The second column is IYZ theta dot, and the third column is IZZ theta dot, and that is a vector, which means this first one would be in the x direction, the next one would be in the y, the last one would be in the z, for whatever body this was. So it doesn't always clean up this nicely. This is just for these simplified problems that we tend to do in undergraduate classes. But in a general sense, this is how you calculate angular momentum. You take the inertia dyadic, you do a dot product or just multiply with your 3/1 angular velocity, and you get a 3/1 vector of angular momentums. So when you're working your homework, I strongly recommend that you write out all of your theoretical descriptions first. For example, K is equal to M times V and H is equal to I times omega, with all of the letters written out, and make sure all these properties are defined. And if I give you numbers in the problem, I need you to take it all the way down to these final descriptions, and you plug in the numbers that are given and you get a number out. If I told you the mass was, let's make it easy. Let's say the mass is 3, that's going to cancel, and then the length is 2, then the angular momentum would be, let's talk a little bit about units. So let's just say MB is 3 kilograms and L1 is 2 meters. Then HBB, well, 3 over, that's going to cancel, and then 2 squared makes 4. And the units now are kilogram. Oh, sorry. Somewhere in there I left out, man, I left it out up here as well. This is why you got to stick around to the end of the video, guys. Times theta dot. Okay. theta dot, there we go. ZB. And let's say that theta dot is 1.5 radians per second. Okay. So this comes out as 3/3 times 2 squared times 1.5. So that's going to be what, 6? 6, and the units are kilogram, meter squared per second. Kilogram, meter squared, times a radian per second. Remember from trig, radian is, it has to do with angles, and it just shows that your motion is following a curved path. So now we're looking at kilogram, meter squared per second. In American units, we tend to describe inertia as pound-foot squared. Okay, so your answer to your homework problems needs to look something like K equals 6, and don't do 6, 4, why not, kilogram meter per second. And then your inertia, your angular momentum would be kilogram meter squared per second. So your answers in your homework need to come all the way down to some numbers that look like this. And gosh, I did it again. Don't forget that these are vectors. So ZB, and let's say that this was KB, sure. And this could be in the YB direction, right? Whatever it comes out to be. Okay, so if you can do kinematics, it's my strong opinion that you should be able to define these momentums fairly easy. The only thing that's really new here is the angular momentum, and you just stick with the equations that we derived in the previous video. You take the values that you have, you plug them into that dyadic, you evaluate it, and you come out with the final answer. That's literally it. Okay, guys, that's it for this one. Where we're going next, we still have to talk about angular momentum about other points, and we need to talk about energy quantities. So those are the next things that we're going to do with momentums. But that's all in later videos. So take it easy, and I'll see you around.